All right, we're on lesson two. Today we're going to be talking about dot products and projections. The dot product is also known as the scalar product. And the reason why is because in the scalar number system, there's only one way to multiply two numbers. In other words, 2 times 3 equals 3 times 2. Order doesn't matter, so it's commutative. It's a commutative process when multiplying scalars. However, in a vector system, there are two primary methods of multiplication, also known as products. One is called the dot product operator, which takes two products and returns a scalar. So, in other words, it takes two vectors with magnitudes and directions and gives you back a number with no direction. So, that's why it's called the scalar product. It's because it gives you back a number with no direction. Um, there's also another product that we're going to cover next lesson. It's called the cross product, and also known as the vector product because it takes two vectors and returns a vector. But we'll get more to that in the next lesson. So, focusing on the dot product, we need two vectors to do a dot product. And for simplicity's sake, I'm going to flatten this into two-dimensional space. This very well works in three dimensions as well. But to make things a little simpler to see, I'm going to go ahead and say this is the x direction and this is the y direction. And let's say that we have some vector A and some vector, let's go with B. And I'm trying to draw B as though it's parallel with the x-axis. So the idea of a dot product, the idea of a dot product is trying to figure out how much of A goes in the direction of B. And so finding how much of A goes in the direction of B is called a projection. And so the way I think about it is if you had a light shining that was directly orthogonal to B, where would A's shadow be projected onto B? And that's going to give us a right angle. And so, as you can see here, we have A being projected onto B. So what I'm going to call that vector, I'm going to draw it here, and I'm going to call that A in the direction of B. So I'll call it A sub B. And what happens next with the dot product is that we take the component of A in the direction of B. So this has some value, right? This is some number. It's a vector still, but it also has a magnitude. And we're going to multiply the magnitude of AB by the magnitude of B. And that's going to give us a scalar because we're multiplying the magnitudes. We're not caring about the direction here. And so, like I said, this projection here, that's the name of it. We call that a projection. Projection. And it's important to know that if we have an angle here between A and B, let's call it theta, that the projection of A onto B, because of trigonometric identities, we say opposite over adjacent or adjacent over hypotenuse. And so if we were looking for AB using theta, we would say that AB is equal to the magnitude of A times cosine, because we're at the adjacent side, times cosine of theta. And to prove it to you one step further, if I divided A over on this side, we would have AB divided by the magnitude of A equals cosine theta. And we know that cosine is representative of a ratio between the adjacent and the hypotenuse. And so cosine is adjacent over hypotenuse. Well, here's our AB, that's our adjacent, and here's our A, that's our hypotenuse. And so this does check out. And so now what we want to do is we want to take this projection of A onto B and multiply that value by b. And so the next step is going to be taking b multiplied by a times cosine of the angle between them. And technically both of these are magnitudes. And this would be representative of taking vector A and dotting it with vector B. So now that we've introduced the dot product, you're not going to want to use the dot as a multiplication symbol anymore because it's going to get confusing as to what it's used for. You're going to want to reserve that for the dot product. So anyhow, this is kind of one of the forms of the dot product. There is one more form of the dot product. So there is a way to describe A in terms of its components. Let's go ahead and say that it has, let's say it goes 4 in the x direction and 5 in the y direction. And because we're in 2 dimensions, we won't have a z direction. And then for B, it looks like it's all in the direction of the x-axis. Let's go ahead and say that B is 6 in the x and 0 in the y. So, this is one way to calculate it. We can find the magnitude of B. And how we would do that is we would take, so the magnitude of B would be equal to the Pythagorean identity of its x component, which is 6, plus its y component, which is 0. And you'll notice here that you just end up with the square root of 36, which equals 6. And that makes sense, because if there's no direction in the y direction, then the magnitude must just be 6. And for A, the magnitude, once again, we would just be doing the Pythagorean identity of the x component, which is 4 squared, plus the y component, which is 5 squared. And that's going to give us 16 and 25. Let's add those together. 16 plus 25 gives us square root of 41. So this would give us the square root of 41 for the magnitude of A. So that's how we'll find our magnitudes for this method. Now this method works great if you're given the magnitudes of the vectors and the angle. So in other words, if I told you what the magnitude of A was, you'd want to use this method, and told you what theta was, and told you what the magnitude of B was. However, the way I wrote it down up here is I gave you components. And so when using components, you're going to want to use this method. And this method is we're going to say that A dotted with B is equal to A in the x direction, A in the y direction, dotted with B in the x direction, B in the y direction. And so what we will end up doing here is we will take, we're going to take A times BX, AX times BX, and that's going to give us some number. So we only multiply like components. We only multiply components with the same subscript. And so likewise, we're going to multiply AY times BY. And that's going to give us some number. And these two numbers, we're going to add them together. And so we have AX times BX plus AY times BY. And we know the values for this. AX is 4, BX is 6. 4 times 6 is 24. Plus AY, which is 5, plus BY, which is 0. So that's going to be, or I'm sorry, times BY, that's going to give us 0. And so 24 plus 0 equals 24. And that is the dot product A dot B, which represents A in the direction of B multiplied by B. So the last part we're going to do here is to prove that the dot product is commutative. Let's say that we did B dot A. So you noticed up here the projection came down to B, and I found A sub B. This time though, what's going to happen is I'm going to project B onto A. Okay, so what I'm doing here is I'm going to shine a light orthogonal to this vector here, the A vector, and I'm going to project B onto A. So that's going to be a right angle. And what we're going to find is there's a projection that is B projected onto A. And likewise, this angle, B projected onto A, is going to equal the cosine, because it's still the adjacent of this angle compared to this hypotenuse. So BA is B cosine of theta. Just like up here, A in the direction of B was A cosine theta. And so B dot A is going to be equal to BA times A. So A times BA is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. Whereas B times A in the direction of B was magnitude of B times magnitude of A times cosine of the same angle theta. Well, because multiplication of scalar is commutative, A times B equals B times A. The magnitude of A times B equals the magnitude of B times A. So that's also why the dot product, how you multiply them doesn't matter, because you're not getting a direction out of it. You're just getting a scalar value. So I hope that was helpful, and I'll see you next video for cross products.